will connect, and it's connected, and now I'll try to write. As you can see, it says here, write data failed, illegal data address. So we try to go past the block size, and this is what happened. By the end of this video, you will be able to implement a Modbus TCP slave on an STM32 microcontroller. So this is the Modbus TCP packet. Basically, it is quite similar to the Modbus RTU1, but we will need to remove the address and the checksum. We're removing the checksum because the TCP packet itself already includes the checksum mechanism, and we are also excluding the address because we are no longer using the RTU mode, and because we're using the Ethernet or the Wi-Fi module, obviously the client will know to which device to send the data. We're just basically taking the function code and the data itself out of the RTU packet, and we're putting it into the Modbus TCP packet. Every server request is basically associated with a function code, and as you can see over here, basically if we want to read up to 20,000 contiguous memory bits, also known as coils, we need to send the function code 1, and for instance, if you want to write more than one holding registers, we will send the function code 16, and that's basically it. Now let's go back to the packet. This is the Modbus application protocol header. So basically the transaction identifier is used to identify a Modbus TCP transaction such that the server will know from which client it has received the packet. The protocol identifier, basically it represents whether we are modifying the Modbus protocol or not, or if you're using the default one or not. The length field basically represents the length in bytes from the unit ID onwards, and that's basically it. I will be using an STM32 again, the Nucleo F756 ZG, and the Mongoose library because I totally hate the lighted IP framework. So I'll open VS Code, and I've already prepared the code. I've already shown you how to integrate the Mongoose and how to switch to the VS Code for STM32 development, so I won't cover these topics again. So basically we're configuring the STM32 as a TCP server because it will be configured as a slave, obviously. So basically we'll configure it to listen on any network interface on port 502 because port 502 is often used in Modbus TCP, and the Modbus, and the Modbus event handler, which will be called whenever the board detects a Modbus event. So let me show you the Modbus event handler. So basically, if we get data from the socket, the minimum payload length that we can receive is 7. So if we go here and we add up all of this together, you can see here that the Modbus application header is 7 bytes. So we have to receive something that is over 7 bytes, obviously. Here I will get the payload length. As you can see over here, if I go to index 4, so 0, 1, 2, 3, 4, I get the length field from here. So, yep. And actually, I've taken this Modbus mini library from the Mongoose code generator and I've modified it a little bit. So, credits to Mongoose. Now, if buff of 6 is not equal to unit ID, we'll simply ignore the request because it's not matching the unit ID, and then we will parse the Modbus packet data unit. So let me go to the packet data unit. Let me show you what function codes we are interested in. So if we look to the function codes again, we are interested in function code 16 and function code 3 because we'll read and write data to the holding registers. Now basically we're calculating the expected buffer length, and here we retrieve the transaction ID, protocol ID, and length. And let me go actually to the function code 3. Here are the function codes used to read the data from the holding registers. So basically we're retrieving the start byte and the number, and we're basically reading the words from the blocks. And I've already declared some arrays at the beginning of the code. As you can see over here, I have the Modbus register out variable and Modbus register in variable. These are just some random values just for testing. And if I go back to our code, reading the words. As I said, we're copying in a buffer, and then we're basically saying whether the transaction was successful or not. So let me show you how exactly will the Modbus read holding register command look like. So I found an article over here. So we'll have the transaction ID, protocol ID, message length, device address, which will be the unit ID, then the functional code. We'll have the address of the first byte, then the number of registers, and then a number of bytes starting from this byte value high A00 and so on. And this will be the response. Transaction ID all the way to functional code. Actually, it goes all the way to this one, address of the first byte of register low. So it basically copies everything it has received until the address of the first byte of the register, or actually the lower byte of that. And then it says the number of the recorded bytes that were retrieved. So I will connect my STM32 to the computer. The Modbus Master software that I will be using is QModMaster. You can find it on Google if you search it for it. I mean, if you say QModMaster, you can find it over here to SourceForge. I will leave a link for everything in the description. Now I'll go into debugging. I'll say run, start debugging. I open real term like this. Yeah, let's clear it. And let me show you first the content of the holding registers. So these are the ones, and I'll start the debugging. So I press continue. Okay, the network is up. This is the IP of the board. I'll open QModMaster. I'll input the IP of the board. So it will be 192.168.137.022 and the port 502. I'll press OK. Set the Modbus mode to TCP, and let's say we want to read the registers first. So I'll say over here read holding registers, and starting from address, let's say 3. So it will be actually from C1D4, because the indexing starts from the desired index -1. So it will be Modbus reg out of mem of 2. I will open the serial monitor for the Modbus TCP, and let's connect. And actually let's read 4 registers. Yep, like this. Set the data format to hex, and I'll connect. As you can see, it says here connected to IP. Then I will read the registers. So basically these are the registers. As you can see, they're perfectly matching. I've already gotten the log messages. Let's debug the response itself. So I'll go back to the packet structure, and as you can see, it says here the transaction ID 02, and then the protocol ID is 0, then the length is B, which is 11 bytes starting from unit ID and so on. Then a unit ID is 01, function code 3, then the baud count is 08 because we have 4 words of 2 bytes, and hence we'll have 8 bytes to read, and these are the values C1D4, 80, 09, and so on. Let me show you the request as well. So I'll go to TX, and it says here the transaction ID and so on, and here we're requesting quantity of registers. Now let's write to the holding registers. So I'll go back to VS Code. I will reset the board. Again, I will connect to the board again. So I will need to write multiple registers. Let's say I need to write the first one 1, 2, 3, 4, then A, D, D, A, and then I don't know, CB, CB, and then 3, 4, 4, 4, 5, 5, and I close this out. I will connect, and I will open the bus monitor. and I'll simply write the data. It says here values written correctly. So let's see the content of the buffer itself now. So this is the buffer itself. As you can see over here, it's added on the watch. I'll pause the debugging and let's check the content. I've started from address 3, hence it should start from index 2, and it says here 1, 2, 3, 4, ADDA, CBCB, and then 3, 4, 5, 5. So that's basically it. Actually, there are some rules to follow when you're using Modbus TCP. For instance, if I go to this page, it says over here, I cannot read more than 125 contiguous memory words because the maximum payload length of the Modbus TCP protocol is 260. And if you're making some computing over here, you have over here 7 bytes and then 8 bytes, including the function code and the data. And since 125 words will be 250 bytes, we will add that with 8 bytes and it will result into 258 bytes, and 2 bytes remain for the length of the data itself. So that's basically it, how it works. The maximum number of holding registers you can write. And also, if you're interested in learning more about embedded systems, I have a free school community in which you can ask your questions about anything related to embedded systems. You will also find a gift over here, but I won't tell you right away what is it exactly. Let's see how does the error checking mechanism work. So the QModMaster doesn't let me write more than 123 holding registers, so I cannot show you how it works. And so what I can actually do, I'll open VS Code again, and what happens if we try to write data past the block size. So I'll restart the board, I'll start the debugging, and I'll open the QModMaster software again. And so let me show you the length of the register out mem buffer. So I have declared it as a macro over here. Let me show you the functional code. Here we're checking if the number of the requested holding registers to write into is greater than 123. And if it's greater, we say the Modbus exception. If I go to this function, to the Modbus exception, we're basically printing the Modbus exception code. And here are the Modbus exception codes. We have the illegal function, data address, data value, device failure, and device busy. Now I'll go back to the function. Basically, we're setting the success to false, and we'll go to error check. And here, actually, what happens, we will construct an error payload. So we'll go to the error check label over here, and basically we're setting the response 7 of, we're adding a SAD to the response of 7. So basically that's how we're constructing the error payload for the client to know that the transaction wasn't successful. So let me show you how this works. I will connect, and it's connected, and now I'll try to write. As you can see, it says here, write data failed, illegal data address. So we try to go past the block size, and this is what happened.